All right. Okay. Okay. Any questions up to this point? Did you find the worksheet on Brightspace? Is that helping you out a little bit?
Oh.
Yes, no?
The conversion tool?
Yeah. Okay, that's helping you out?
Yeah.
Making sense?
Yeah.
Okay. Uh. I was informed last year when I taught this course that the students didn't get textbooks in high school. Is that accurate?
The guy takes.
You got textbooks. But my kids don't get textbooks when we go to Western, so what I do is I put worksheets on there, so I'll put some worksheets on there. Okay. Oh, goodness. Okay. All right, so this will be chapter 2. In this chapter, we're going to be talking about atoms, molecules, talk a little bit about the periodic table. Any questions up to this point? Anything? Don't ever be shy to ask a question, okay? Just seriously. When I was in graduate school, the last time I went, it dawned on me sitting in classes that I don't care what anybody thinks about me. I want to get out of this. I want to graduate and get out. Yeah, what's up, Olivia?
Are these PowerPoints up on Brightspace?
Yes, they should be.
Oh.
Have you seen them?
Mhm.
Yeah, they should be. And I think what I have is I have the syllabus. I think I have chapter 1, Olivia, then I think I have the worksheet and then chapter 2. So in Brightspace, there'll be the lecture portion and then the laboratory portion.
Okay.
So if you have problems, let me know, all right? We'll get it figured out. All right, good. So far, so good? All right. So in this chapter, we're gonna be talking about the atom. We're gonna talk about the structure of the atom, all right? And we'll probably do some more conversions a little bit later. Any questions on the conversions? If you do, I have 3-4 hours after class. You can stop by anytime, just talk to me. Does that make sense? And I have office hours, but if they don't work for you, just show up. All right. I don't leave this building until I go home. For the most part. I'm almost, if you see, I eat my lunch in my office. I'm in my office all the time to be accessible to you all. Okay. Chemistry can be kind of hard. And my goal is that I don't ever want to see you in this class ever again. I want to see you next semester. So that's my goal. All right. So don't ever be afraid to come and ask me for help or anything. All right. So the atomic theory. Bless you. This is all assembled by a guy named John Dalton. He was an Englishman. Now, a lot of these ideas had been floating around, okay? And what he did is he had just actually compiled them and brought them together. Now, what chemistry really is it's a study of matter. That's it. What we do is we enjoy studying matter, okay? And there's 2 types of chemists in this world. There are those who create new forms of matter, like Dr. Baldwin, half of your folks is lab instructor, and then myself. And I destroyed matter. So Dr. Baldwin synthesizes and makes things. When I got my PhD, I destroyed it by blasting with an enormous laser. That's what I did. So I destroyed matter. But that's what chemistry is mostly concerned about, is matter. All right. And matter is composed up of atoms. All right. Now, atoms, the idea of an atom was thought of by the Greeks. Okay. My wife was born and raised just north of Greece, and I've sat on the northern shores of the Mediterranean Sea and overlooking it, and I can just imagine these Greeks, and they had a thought experiment. All right. They had this thought experiment that if they had something and they ripped it in half, they took one of those halves, they ripped that in half, ripped it in half, ripped it in half. Could they get to a point when they were holding that piece of matter that it was no longer divisible? They could not rip it apart any further. Does that make sense? Right? If I were to take a piece of paper, rip it in half, and rip it in half, and rip it in half, is there a point where I could rip it no longer? And they said yes. And they called that the atom. Should be fairly similar to Adam, the first man. Does that make sense? Right? So That's where it came from. All right, now, this was Dalton's atomic theory. Now, it's not accurate, okay, but this is what he did. So these ideas had all been floating around. All he did is he compiled them together. So elements are composed up of identical atoms. Right? So all the hydrogen atoms look the same, all the oxygen atoms, all the gold atoms, all the mercury atoms, all the rubidium atoms. That's not entirely accurate. We'll find out that it's a little bit different. Does that make sense? Right, but at this time, they didn't know anything about these things called isotopes. Right, so they didn't know about that. Differing atoms combine to form compounds. Right, so for example, water is going to be 2 parts hydrogen, 1 part oxygen. How they knew about this is that they would take a compound and they would try to destroy it. They would try to burn it. They would use heat. They would any possible thing they could possibly do. They tried to destroy that compound until they got to what it could no longer be converted to anything else. They said, oh, this must be an element. Right? Once electricity came about, once they discovered electricity, whoa, they had a lot of fun destroying a lot of these compounds. Right? And then lastly, atoms of one element cannot be changed into atoms of a different element. We know this is not true anymore, right? If I'm not mistaken, well, I know up in at Michigan State, there's a nuclear reactor. In that case, they convert one form of element to another form of element, right? At least I believe Michigan still gets some of its electricity from nuclear reactors, correct? Pretty sure that's accurate. I know the state of Minnesota I came from, they do. It's up in Monticello. But this is going to be atomic theory. Any questions on that? We good? All right. Okay, so as I said, the Greeks were the first ones to propose the idea of an atom. All right, so what is the structure of the atom? Well, they knew certain parts of the atom. They knew some of it was positive, some of it was negative. All right. But they didn't know what it looked like or how it went together. So there was somebody called Lord Kelvin or William Thomson. And I can just sort of envision how this all came about, right? Old Bill Thompson there spent the day working in the lab. His wife invited the neighbors over, and being a typical scientist, he didn't want to have any neighbors over, but she wanted to socialize. I'm just saying, kind of like how my family is. He's sitting there, the neighbors talking to him, blah, blah, Bill, and all Bill's thinking about, William Thompson's thinking about is the experiments he'd done that day and how he was trying to come up with the structure of the atom. Okay? The main course comes out, he's eating the main course. He's sitting at the table. He doesn't want to talk to anybody. He just wants to sit and think about his science. All right? His wife brings out then, it's dessert time, his wife brings out plum pudding. Now, do you know what plum pudding is? It's pudding with raisins in it, essentially, like that. I always kind of think of a blueberry muffin, is what I think about. She brings out this plum pudding. He's looking at it, and the pudding is going to represent this thing, which is going to be what they would call ether. Right now, ether was a generic term that scientists back then used for a substance they didn't know what it was. Just a generic term. And he's eating his plum pudding. He's thinking, oh my goodness, eureka! The pudding is just like the positive stuff. It's the positive thing that holds the negative electrons there. Does that make sense? A better analogy would be a blueberry muffin. The muffin portion of it would be the positive ether, and the blueberries would represent the negative charge or the electron. Does that make sense? And he said, this is how an atom is held together. You got this whole bunch of stuff we call ether. That's going to be the positive material that holds a negative electron in. Does that make sense? And that's what they thought that the atom was, the structure of the atom. Or imagine a chocolate chip cookie, the cookie portion is gonna be the positive, the chocolate chips are gonna be the electrons, the negative electrons. Does that make sense? You with me? And that's what he thought the structure of the atom was. Well, Millikan comes around a little bit after, and he's gonna, what he does is he gives the electron its charge. Now, they knew that it was negative, okay? But how negative is it? Right? So we had a qualitative measurement. We knew that the electron is going to be negative, but just how negative is it? And so Millikan had done this experiment. All right. And what he did is he took some oil and he atomized it. So he put it into a really fine mist, an extremely fine mist. All right. Some of that atomized or mists of oil droplets, really itty bitty tiny droplets, fell through a hole. Now, of a plate. Now, there were two plates in the experiment. This was kind of at a vacuum. And these two plates were charged with a potential, right? So that's what the positive and negative is, that there's going to be a potential here. And what he did is he charged these oil droplets. He could then hinder the fall of the oil droplets based on the potential he put into the, he ionized the charge, he ionized the oil droplets with X-rays, basically putting a bunch of electrons around them by hitting them with X-rays. He charged them, then he could hinder the fall of those oil droplets with a potential. Based on that potential, he could, as I said, he would hinder the fall of those droplets, all right? From that, he came up with a mass to charge ratio, all right? And he found out that the charge of an electron is 1.602 times 10 to the minus 19 coulombs, okay? We won't use that number in this class. If I happen to see you in physics, we'll use that number quite a bit in physics too, but not in chemistry 1, okay? So by varying the potential on these plates, he could hinder or adjust the fall rate of the ionized oil droplets. I did this experiment, oh my goodness, a long time ago. It was an absolute pain to get set up. It was very difficult. But he came up with the mass to charge ratio. All right. We're good? So far, so good. Now, notice 5 years prior, Lord Kelvin had come up with the plum pudding model. Millikan gave us the mass to charge ratio, and then Rutherford was the one that actually gave us the true structure of the atom. Okay, and here's what he had done. And his name was Ernest Rutherford. I believe he was Australian. I think he was Australian. I think he did his research in England, though. I think he was Australian. What he had done now, and this is kind of interesting, all right? He had used alpha particles. Now, what's an alpha particle? Well, an alpha particle is a helium nucleus. All right? Now, they didn't know what a nucleus was, right? But they knew they were generating very, very small positive particles, right? So he took this beam of alpha particles, the nucleus of a helium atom, and he was going to bombard a piece of gold foil, okay? To prove Lord Thomson was correct on his structure of the atom. And what his hypothesis was that if Kelvin is correct on the structure of the atom, that the alpha particles, when they hit the gold foil, should go right through the gold foil and hit this zinc sulfide fluorescent screen. the screen would fluoresce when it was hit with or bombarded with alpha particles. Does that make sense? Understand the experiment? So the idea is that these alpha particles should blast right through the gold foil and hit this fluorescent screen. And for the most part, that's what he saw. But what he also saw was he saw these alpha particles, they hit the gold foil and then they would deflect. So they ran into something massive. Does that make sense? Right? If I'm simply to walk to the door, right, let's say my eyes are closed, if there's nothing impeding my travels to the door, I walk a straight line. Does that make sense? But if I'm going to run into something, I run into a table or run into a person, I'm going to get deflected. Now remember, Thomson thought that the atom was a bunch of this positive ether stuff that held these little electrons. So everything should just blast right through it. But they were being deflected, which meant that they were running into something massive. They were colliding with something. So what that told us was that Lord Kelvin or William Thomson was wrong. That is not the structure of an atom. Does that make sense? So he was wrong. Thomson was wrong. Rutherford said, this cannot be the structure of an atom. And this is sort of a cartoon. Okay, so what we have here, going from left to right, is we have a beam of the alpha particles, right? So the helium nuclei. Over here, these spheres, what they represent is they represent the gold atoms that make up the gold foil. And you can see that what happens is some of these alpha particles will hit these itty bitty tiny nuclei and they get deflected. That makes sense? What Thomson theorized is that these little nuclei are no longer, they weren't there. It was just, this is going to be your atom. It's made up of positive substance with electrons embedded into them. But that's not the case. What it is is this is the nucleus of a massive particle, and the alpha particle will hit it and get deflected off of it. All right? That makes sense? So the alpha particles were deflected by the nucleus of the gold atoms. And so at this time, the cell had already been discovered, right? They microscopes have been around for over, at this point, a couple hundred years almost. And so they used the exact same terminology as they did in biology, right? Biology is a much more developed science than chemistry was. About the late 1900s, they were starting to get out of the alchemy phase, all right? They're actually getting to do real chemistry. So that's where it came with the nucleus, right? And so this must be kind of like a cell, right? We're good? All right. So here's what they thought. Here's kind of a depiction of what the atom looks like. Okay. So you got this nucleus right here. Okay. And what surrounds the nucleus is going to be these electrons. So the charge of electron is going to be negative. We know it's a negative 1.6 times 10 to the minus 19 coulombs. But we're just, for the rest of your chemistry career this year, we're just going to look at the electron being negative 1. Okay? That's it. We don't worry about the actual charge. We're going to say it's negative 1. Okay? And what's the proton? The other subatomic particle we need to worry about is going to be the proton. Right? So a proton is going to have a positive charge. Right? Its charge is going to be a positive 1.6 times 10 to the minus 19th coulombs. It has the same charge as the electron, just or same magnitude, just opposite sign. Does that make sense? And you notice that the mass of the electron is 9.1 times 10 to the minus 31 kilograms. You don't have to memorize that number, right? Don't memorize constants. I'll give you all the constants. You don't need to memorize the constant. The mass of the proton is 1.6 times 10 to the minus 27 kilograms. The mass of the proton is about 1,800 times more massive than that of an electron. That's just something to keep in the back of your mind. Does that make sense? That the proton is much, much, much more massive than that of the electron. Now, it was very easy to discover the electron because it's negatively charged. Likewise, it's very easy to discover the charge of the proton and its mass. But there's one more subatomic particle we need to be concerned about. That one was the most difficult to discover. As a matter of fact, it took 40 years to discover it, and that's the neutron, because it doesn't have any charge. How do you find something that doesn't have any charge? It's hard to do. All right. So it has no charge and it contributes to the nucleus. All right. The mass of an atom is primarily going to be the neutron and the proton. Okay. Now, which one's bigger, the proton or the neutron? The neutron is by you know how much? The mass of an electron. So guess what a neutron is? It's a proton and an electron together. All right. Now, just to let you know exactly how nerdy I am, not that the clothes would give it off, the calculator in my breast pocket here. I mean, the scream's nerd, right? I just need a pocket protector. And goofy black ring glasses, I have them upstairs, just to give you an idea. I would lose sleep at night wondering what kept the nucleus together when I first started teaching. I was so fearful that some students were going to say, what holds that nucleus together? Do you know? So we'll talk about it. Because it's amazing. This nucleus should not hold together, right? Because light charges should repel. Correct? Light charges should repel. Why does the atom hold together? What should happen is these electrons should feel or sense the protons in the nucleus and should suck right up, and matter should basically be not even exist. Right? If we look at that. What holds a nucleus together, this is just extra, I'm just giving this to you, I'm not going to ask you a test question on that, is let's say we look at the alpha particle, all right? So we're going to have a proton, another proton, and then here we're going to have a neutron. And we're going to have another neutron, all right? Now, what this neutron is, it's actually made up of a proton and an electron. That's what the neutron is. And this is what nuclear chemists or nuclear physicists theorize is what's holding the nucleus together. Is that if this electron goes over to here and this electron goes over to there, that turns this neutron into a proton, this proton into a neutron, this neutron into a proton, and that proton into a neutron. Does that make sense? Can you kind of see that? And they theorize what happens is that these electrons oscillate back and forth between a neutron and a proton, and that's what they think is what holds the nucleus together. But they don't know. But we still take advantage of it, right? Dave, you know how a cell phone works? Anybody? Well, the 5,000 students I've had in my life, there's only been one student that could literally tell me how a cell phone works. But we still use it. Does that make sense? We're not entirely sure what holds this thing together, but we take advantage of what it does. And so this force here is what's called the strong nuclear force. All right, well, we might talk about that a little bit later at the end of M2. So far, so good. We'll talk about the electrons going around. Now, up to this point, we are no longer going to be concerned about the electrons within the nucleus. All right, we're only going to be concerned about the electrons outside the nucleus. Okay, but this is what they theorize is holding the nucleus, holding nuclei together, or is considered a strong nuclear force. All right. We won't talk about the electrons in their orbits, and we'll talk a little bit why don't they just collapse into the nucleus, because the nucleus is positive, the electrons are negative. We'll talk about that a little. So the charge of the electron and proton are equal in magnitude, just opposite in charge. And this is what we're going to start talking about, what makes chemistry difficult. And I mean, I don't just mean in terms of calculation, but what makes it difficult, right? So if you're reading your textbook and you see a period at the end of the sentence, right? If you see a period at the end of the sentence, if you look at the diameter of that period, you can align 1,000,000 atoms along that period. What I mean is there are a lot of atoms, and they're really, really, really small. So it becomes a very abstract science, which makes it more difficult. If you were to take Dr. Balser, Dr. Wyman, or Dr. Baradovich's biology class, and they're in there talking about cells, hey, they could whip out a slide, put it underneath a microscope, and boom, you can see the cell, can't you? Right? You can observe it. It's not near as abstract because you can see it. I can't show you an atom. If we had an AFM here, I could show you the results of an atom, right? I could show you the electric field, but I can't, of the electric field from the electrons, but I can't actually show you an atom. I can say, hey, look, here's an atom. I can't do it. It can't be done. That's what makes it hard. This is another thing that makes chemistry hard. If my thumb were if to give you a size scale, I want to give you a size scale of this. If the nucleus was the size of a grape, the nearest electron would be a mile away. What would be in between the nucleus and that electron?
Energy?
Nothing. There's nothing. There's going to be some type of energy, but there's nothing. There's nothing of tangible mass or feeling. There's no air. There is nothing. Absolutely nothing. There's nothing. So the volume of an atom is going to be 99.999999% of empty vacuumous space. Nothing. Not air. Nothing, because air is made up of atoms, right? So there is nothing. Okay? Now, are we made up of atoms? Yeah. Is my fist made up of atoms? Yeah. So I know Cooper here. I know his brother. I don't like his brother. But let's say I'm going to hit Cooper. My fist should go right through his face, right? Because I just told you atoms are mostly empty space, right? Should we see what happens? No, I'm just kidding. What gives mass its tangible feeling is not just the atoms, it's how the atoms bond together. When you feel something tangible, what you're literally feeling is the results of these atoms bonding together. We're going to spend the next couple of weeks, week and a half, talking about the atom. But if atoms didn't bond, this class would be over in the middle of September. We're going to spend the majority of the time talking about how these atoms bond together. And that's what gives mass or stuff. That's why my hand will not go through this table, because of the chemical bonds in my hand and the chemical bonds in this table. That makes sense? It's how the atoms come together is what gives mass that feeling, or matter that feeling. Does that make sense? Some of you are probably wishing, man, I wish this class would be over in the middle of September. Sorry, it just isn't. And so that's what chemistry really studies. I don't care. It's always about the chemical bond. I don't know so much about biology, but I can certainly tell you physics is about two things. If you got to take physics, it's about two things. It's about force and it's about energy. Your brother had it, he's 2 to 4. That's all physics is. We go to 2 points in physics. We first go to force, then we go to energy, and that's all physics is. In this class, in chemistry, 95% of the time, it's about that silly chemical bond. That's what we look at. That's where we're always gonna go. That's where we feel comfortable is in that chemical bond, talking about that. Makes sense? So kind of a big overall picture. Have you ever, I kind of a goofy story. Like I was newly married, and I had not read through all the Holy Scripture yet. I had not read through it all. And so I remember I went to my wife and I said, "What book should I read next?" She said, "You should read First Samuel." Oh, I'd never read First Samuel. Any of you read First Samuel before? Yeah, it's a phenomenal book. It's amazing. So I read through First Samuel. She said, "Oh, what'd you learn?" And the way my brain works, I always look for some big overarching theme in anything, and I just try to start filling in the holes. Does that make sense? Looking for the little detail. I read First Samuel and said, "Huh, well, Israel should have had God as their king and not Sam and not Saul." Right? I mean, if you read First Samuel, what you read is they wanted to be like all the other nations and have an earthly king, and the king they should have had died. Right? Well, so in chemistry, an overarching theme is going to be bonding. When you look at that, you want, and I always want to tell you where we're going. I don't want to leave any mystery at all for you folks. Where we're ultimately going to go towards the end of the semester, this thing called electronegativity. We're going to look at how that electronegativity determines the chemical bond. Okay? All right. So we'll get to that in a month or so. All right, but that's kind of where we're going to go. I do apologize. Chemistry 1, I think, is somewhat confusing because every week we change a topic. It's how it is. I apologize. Chemistry 2 is a little bit harder, but we don't change topics every week. We sit on a topic for quite a while. In chemistry 2, I think we just cover. We'll do intermolecular forces, kinetics, intermolecular equilibrium will be there for almost a month, and then we do thermal and electrochemistry. It's not too bad. And if we have time, we'll do some nuclear chemistry, which is fun. Here, we'll do 14 different topics. Every week it's a different topic. All right. Does that make sense? Well, an atom is mostly going to be empty space, not air. It's vacuum. I mean, there's nothing there. Here is periodic table. This is the periodic table. You get I'll give you one of these for the exam. I'll give you one for every exam, actually.
Oh, yeah.
So we're gonna start talking about this a little bit now. We'll spend a lot of time talking about this periodic table. A lot. Everybody got one? And if you forget it, forget to bring it to class or you lose it, I'll give you another one. It's not a big deal. Typically, we would have a classroom with a huge periodic table in it, but this is the second year in a row I've taught chemistry without a periodic table. It's hard to do. It's like teaching anatomy without a skeleton. It's just very difficult to do. Every one of these boxes represents a different element, right? What differentiates so for example, if you look at alchemy, if you look at the history of chemistry, they spent a long time trying to convert lead into gold. Why is that? Well, gold is a much more valuable metal gold is much more valuable metal than lead is. Why can they not do it? What distinguishes lead from gold? Right? What distinguishes hydrogen from helium? Why is it that hydrogen is flammable, but helium is not? Right? So what distinguishes one atom from another? What distinguishes us individually?
Well, we have DNA, right? That's what distinguishes us, correct? So in essence, what is the DNA of the atoms, right? What distinguishes one atom from another? And that's what we're going to try to answer this question, all right? To do that, we're going to look at these things called isotopes, all right? So an isotope is an atom that has the same atomic number, but it has a different mass number. So if you look on your periodic table, you see the letters in the middle, or letters in the middle. That's the symbol. That's the abbreviation for the symbol. You see the number above. So example, lithium, which is the third element, you see that 3, that is going to be your atomic number. The number below it, 6.941, that's going to be your mass number, all right? Okay, we'll talk about why that the mass number is not a whole number in a little bit. Good? So far, so good? Makes sense? So now the atomic number, that number at the bottom, is going to be equal to the number of protons and the number of neutrons. I believe it's in the next chapters where we'll discuss, well, why, if we're talking about the number of protons, number of neutrons, why is lithium 6.941? Why isn't it just 7? I mean, these numbers are quantized. I can't have a half a proton, I can't have half a neutron. We'll talk about why they have those decimal points. So the atomic number is going to be equal to the number of protons, right? The mass number is going to be equal to the number of protons plus the number of neutrons. So the atomic number is going to be equal to the number of protons. The mass number is going to be equal to the number of protons and the number of neutrons. The parts are good? It makes sense? So for example, if you look at potassium, it's going to be the 19th element. So it's going to have 19 protons, all right? This number, 39, is going to be the number of protons and the number of neutrons. So if we have 19 protons, how many neutrons do we have? 20. That makes sense? We have 20. In this case, we look at argon. So here, argon has 18 protons. It has a mass of 40. All right. So this is how it's written symbolically. It's not how it is on a periodic table. So it has 18 protons and it has 40 as its mass number. So it's going to have 18 protons and 22 neutrons. Is what it's going to have. Does that make sense? Right, so we can do this for hydrogen. All right, we can look at these symbols. So if you look at hydrogen, if we write the symbol for this, it's going to be H, right? It's going to have 1 proton and its mass is going to be 1 as well. That makes sense? You look at that on the periodic table, correct? So it's 1 and 1. If you look at nitrogen, and how many protons does it have? 7? Yep, exactly. Good. 7, and its mass is 14. Right? Making sense? Isn't this thrilling? It's boring. I should have had that memorized, but I don't. Next one's zinc. Number of protons is 30, right? And its mass is 65. 65. That makes sense? All right. So this will have, if we look at hydrogen, right? If we look at hydrogen, the number of protons it has is 1, right? Number of neutrons is zero. It doesn't have any neutrons at all. Doesn't have any neutrons at all. And if you want to look at the number of electrons, since this is a neutral species, it has to have one electron. Okay? Whatever atom is neutral, it will have the same number of electrons and the same number of protons. Okay? So if we look at nitrogen, it will have 7 protons, 7 electrons, and 7 neutrons. Does that make sense? What ours would do? Look at zinc. It's going to have 30 protons, 30 electrons, and then 35 neutrons. So are we able to answer what this differentiates one atom from another? What do you think it is? Close. Now, if you look at hydrogen, what does the 1 represent? Protons. What does the 2 represent in helium? Protons. What does the 3 represent in lithium? Proton. So the answer to this is the number of protons. Now, we're going to look at some examples in a few minutes where we haven't looked at any isotopes yet. All we've simply looked at is actually the most, well, these are the most common isotopes on the periodic table. All right, we're good? So far, so good? All right. Now, let's pick on little hydrogen here, all right? Now, hydrogen has 3 isotopes. Oops, I gotta move this over here so I can see this. All right, because I don't need to see that. Hydrogen has three isotopes. One is hydrogen. Second is deuterium. And the third one is tritium. All right. If we look at hydrogen, all right, so we just look at hydrogen. This will be for hydrogen, all right? We've already looked at that. That's going to be 1 and 1. Okay. So it's going to have 1 proton. It's got 1 proton, 1 proton. That's all it's got. It doesn't have any neutrons. Does that make you good with that? Mm-hmm. If we look at deuterium, all right. This is going to have 1 proton. It's still going to have 1 electron, but in this case, it happens to have how many neutrons? 1, yeah, 1, because the mass is 2, yeah. So it's got a proton, it's got to have a neutron. Mm-hmm. Makes sense? Look at tritium. That's going to be 1, 3. Number of protons it has is still going to be 1. It's neutral. If it was charged, we put a charge there. It has 1 electron. Okay. And how many neutrons does it have? It has 2 neutrons. Now, if you go and look at helium, just look at helium. Helium is going to have 2 protons and 2 neutrons, right? So it happens to have the same number of neutrons as tritium, but what makes helium special is it only has 2 protons. That's it. Right? Deuterium is kind of an interesting isotope of water, of hydrogen. If you could make, obviously water is going to be 2 part hydrogen, 1 part oxygen. But if you decide to use 2 parts deuterium and 1 part oxygen, that's what's called heavy water. That's used in nuclear reactors. So that would be the water in between the control. Well, you have fuel rods and you have control rods. So the fuel rods are what kick out neutrons, right? So what happens, how a nuclear reactor works is the breaking down of the nucleus releases a tremendous amount of heat. That's going to heat up water, cause a turbine to spin, and but deuterium or heavy water is used a lot of times. So how they hinder the amount of neutrons being formed is either use control rods, which is one way, something to absorb the neutrons. Also, you can also use heavy water as well. That's where deuterium is used. Any hunters in the group? You like to hunt? You ever heard of Trigicon scopes? Very expensive scope where the reticle is lit up. It's through phosphorescence. They have radioactive tritium, which emits out an electron, and that is going to cause the phosphorescence. They're great when you're old like me because the reticle is well lit, but the half-life of tritium is only going to be about 13 years. After 13 years, that reticle degrades and so on. But that's what that can be used as. It's was used a lot in watches to make them glow in the dark. Used quite a bit. Another element that has really interesting isotopes is carbon. So carbon is a really neat element. If you ask Dr. Baldwin what his favorite element is, I guarantee he's going to say carbon. It's his favorite element. It's not mine, but it's his. So carbon has some interesting isotopes. So you can look at carbon-12. Which is the most common of the isotopes. If you look on your periodic table, you'll see that it has a mass of 12.01. We'll talk about the 0.1 later, okay? So it's going to have 6 protons, 6 electrons, and then 6 neutrons. Okay? Now, another isotope of carbon is what's referred to as carbon-13. Okay? Carbon-12 is primarily, makes up the majority of all the carbon in the universe. It's about 9 of the carbon, 99% of all carbon is going to be carbon-12. About 1% is going to be carbon-13. So that's going to have, once again, it's going to have 6 protons. It has to have 6 protons because it's carbon. Number of electrons is going to be 6, right? How many neutrons will it have? 7. Yeah, exactly. It has 7. Exactly. The last isotope of carbon, which you hear quite a bit about, is carbon-14. Anybody know what carbon-14 is used for? It's what carbon does when it's lonely. It dates. It's used for carbon dating. That's kind of funny, isn't it? That's funny. Here's kind of because it's lonely, right? It wants to date. Good grief. Or carbons. It's all by its lonely. But this is what's used for carbon dating. So if they're going to carbon date something that was once alive, they use carbon-14. That's the isotope they look for. And its half-life is about 5,300 years. Something about that. Right? We'll talk about half-lives in a little bit. So this is going to have 6 protons, 6 electrons, and the number of neutrons is going to be 8. That's exactly right. This is a kind of a unique stuff. This is really unique carbon. This is actually made in the upper atmosphere, up in the stratosphere, when lightning hits oxygen and nitrogen together. A nuclear reactor between oxygen and nitrogen. It's crazy. It's absolutely amazing. But that's where they think carbon-14 comes from. Yeah.
Are the protons or electrons always moving the same way?
Yes, as long as they're neutral. As long as we have a neutral atom. If we have a charged atom, then it cannot be equal. Very good question. Very good question. Very good question. Does that make we're good? But if we have something charged, Reagan, then it cannot be equal. And so if it's going to be positive, it has to have more protons. If it's going to be negative, it has to have more electrons. Good. Does that make sense? But right now we're living in a happy little world of chemistry where everything is neutral and everything's just all happy and hunky dory and really quite bored. We're good? All right. Okay. All right.
ready to do a problem now? Okay. Uh, yeah, we'll just do a few of these. Okay, so we got a symbol, protons, got neutrons, we got electrons, we got the mass. This may be called the mass number or the atomic mass, okay? And what we're gonna do, how we're gonna do these, we'll just look at a column and we'll go down, okay? Okay. Now, just as we saw in the isotopes, the mass number does not have to match the one on the periodic table. Okay, it does not have to match that. That mass number that you see in the periodic table is what's called a weighted average of all the isotopes that exist. Okay. So Br, anybody know the name of that symbol? That's bromine. That's exactly right. That's going to be a halogen. All right. How many protons? So we got up here, we got 79. Ooh, oh my goodness. Come on, Mikey. Let's get it together. Almost like I'm looking forward to the weekend. I always am. All right. 79. What's going to be our number of protons? 35. All right. Number of neutrons. 44. 44. Now, something you'll notice early in the periodic table, the smaller atoms will have about the same number of neutrons and protons. As the atomic number gets greater, those atoms have more neutrons and they need protons, and that's to stabilize that very strong positive proton charge. Really, really interesting stuff. How many? Now, we're going to say this is going to be, we don't have any charge up here, so the number of electrons is going to be, right again, it's going to be, sorry, so it's neutral, so it's going to have how many electrons? 35, yeah, exactly. And the charge would be placed, in my opinion, you asked a good question. So the charge would be located right here. And we don't have a charge here, so we're going to say it's neutral. All right. And the mass number is going to be, or the sum of those two. All right. Okay. So now we're going to do the second column right there. Carry this over to here. So we have over here, this is going to be 25, and this is going to be 30. Okay. Hide the red. Okay. Well, let's just do something kind of, we can go in, well, what's going to be the symbol? We'll do that. So 25th element is Mn, which is manganese. Right, so that's going to be Mn, right? Number of electrons. It's got 25, that's exactly right. And the mass number is going to be 55. Yep, exactly. And so that's going to be 55 right there. Okay. We got 64, 48. All right, so what's going to be our element? GB, right? Wait, no.
CD.
No, I'm sorry, I got this wrong. I got this wrong, don't I? Oh my goodness. I'm really ready for the weekend. This is 64, and this is 48. Sorry about that. All right, so we're gonna assume this is gonna be a neutral element because we don't know anything other than that, right? So how many protons do we have? We have 48, right? Sorry. So 48 element is going to be cadmium, right? That's gonna be our cadmium C8 or CD. Okay.
The mass number of this is going to be 112? Making sense? Easy?
Mhm.
Boring? It's easy though, right? And it's really easy stuff. Oh, then we have 86. What's it gonna be? 86. 222. There we go. All right. Now let's see here. We'll do the easiest one. So we've got 86 electrons. How many protons are we gonna have? Gotta have 86, correct?
Mhm.
Right? What's the 86th element on the periodic table? 86. Radon. Yeah, radon. It's that nasty noble gas that seeps through people's basements that causes cancer. Jackson County is lit up with radon. Tons of stuff in Jackson County. I mean, it's ridiculous. Mass is 222. And then what's going to be the number of neutrons? 126, is that what you got? 6. Maybe it's 136, right? Maybe it's 136. Yep, 136. Good?
Mhm.
All right, we'll finish this up and then call it a week, all right? Number of protons, so this is gonna be 82. This is 207. All right. Any questions up to this point? Number of electrons is 82. Number of neutrons is going to be 125. 125. 82nd element. Which is what? You know what element that is?
No.
Yeah, lead. 2. 125. EV is lead. 207. All right, cool. All right, we'll see you on Monday morning at 7:45.
Yeah.
Yes.
Snow.
You a morning person?
Surprising. Ish.
Good, well, good. Yeah. I'm not a